Welcome back to Fast Pace. This video program provides support material to help you pass the ASE Automotive Electrical Test. If you've not already done so, open the support package. Remove the mini-test labeled Electrical Systems and the answer sheet. Stop this tape and take the test. Record the answers in the proper place on the answer sheet. Then return to this video and we'll analyze the questions one by one. Successful electrical troubleshooting requires that you develop certain skills not normally associated with mechanical repair. Because of the absolute need to understand these skills and procedures, we will deviate momentarily from the normal question and answer format we use in other programs. Of course, once the initial technical information has been presented, we'll resume our normal routine, helping you with typical electrical questions found on the ASE tests. The skills and procedures we spoke of break out into schematic reading, developing a working knowledge of electrical test equipment, and electrical circuit diagnosis. Although we will quickly cover these areas, don't forget to use the task and reference sheets to really drive home these important points. To begin diagnosing electrical problems, we need a way to organize the vast amount of information about the electrical contents of vehicles. Hence, the use of schematics, which pictorially represent the physical components in each circuit. Each symbol in the schematic represents a distinct electrical component. The minimum components necessary for a circuit are a power supply, in most cases the battery, conductors, and a load device. However, to control a circuit, a switch is typically used. To prevent fire or damage to the circuit from overload, a protection device such as a fuse, a fusible link, or a circuit breaker is necessary. As more loads are added to the circuit, they can be wired either in series, parallel, or in a series parallel manner. Knowing how the loads are wired is an important step in troubleshooting because the expected voltages will differ depending upon the type of circuit configuration. Some failure patterns are unique to a particular circuit configuration. In the simple series circuit, we know that the battery typically has 12.6 volts. With one load in the circuit, under ideal conditions, all the voltage is used up by the load. If another load of equal resistance is added to the circuit, each load shares the source voltage equally. Unwanted resistance at any point in the circuit, such as a corroded ground connection, acts like an additional load in the circuit, reducing voltage to both loads. If the same loads are wired in parallel, each load receives full battery voltage. If extra resistance is present in a leg of the circuit, only the load in that branch of the circuit receives reduced voltage. A series parallel circuit combines series circuits with parallel circuits. Schematics take the guesswork out of troubleshooting, provided you read and understand them. For instance, look at this relay. You can see which wire terminals are for the higher amperage circuit and which are for the low amperage control circuit. If incorporated into a circuit and the load didn't work, we would know from the schematic the terminal X of the relay should have battery voltage. Y terminal, when grounded, completes the circuit, causing the contacts to close, thus completing the higher amperage circuit. If we have feed voltage at the relay and control circuit ground, but the load still didn't work, we would look for a defective relay, a defective connector, load, or conductor. A fused jumper wire can be used to manually jump the circuit to further pinpoint the problem area. Electrical circuits usually fail in three ways: opens, shorts, and high resistance. We can use several tools to diagnose these conditions. If a circuit has an open, such as a broken wire, defective switch, or a blown fuse, we can locate the problem area using a test light, an ohm meter, or a voltmeter. With the test light, we can check for the presence of continuity. We're actually testing for available voltage. In an incomplete circuit, if there's continuity from the positive side of the battery to any point in the circuit, when probed, the test light will light. On the other side of the break, the test light does not light. If we do these same checks with a voltmeter between ground and the points in the circuit, we see full battery voltage, an indication of available voltage. At the break, the meter shows 0, indicating no voltage is left in the circuit. Defective fuses, switches, loads, or for that matter, any electrical component can be isolated as a cause of an incomplete circuit in this manner. The technique used to isolate opens with an ohm meter or a self-powered test light's a little different, but it's just as effective. These instruments have their own power supply, so remember to remove the power supply from the parts of the circuit being tested. Each part of the circuit can be individually tested for continuity with the ohm meter or the self-powered test light. When the open component or conductor is tested, the ohm meter will indicate infinity, or the test light won't light. While the ohm meter can indicate the amount of resistance of components being tested, the self-powered test light cannot. If you're testing components designed with high internal resistance, the self-powered test light may not light. Therefore, testing these components with a self-powered test light is not recommended. Shorts are diagnosed using different techniques. Shorts come in two different varieties: shorts to ground, in which a load or circuit control device is bypassed, and shorts to power, where some other power source is feeding a circuit. If a short to ground occurs before the load device, usually the circuit protection device will blow, so that when you see them, they are already dead circuits. Fuse replacement will cause the circuit to conduct more amperage than designed for, and it'll blow the fuse again. The ohm meter is a very useful tool when troubleshooting an open. However, when troubleshooting a short to ground, it's practically useless. Instead, use a short detector or a resetting circuit breaker attached to alligator clips. When the breaker's closed, there's current flowing in the circuit, creating a magnetic field. When the breaker trips, the magnetic field collapses. When the breaker resets, the field is created again. This pulsing field can be detected with a field indicator or a compass. Moving the indicator around the circuit until you reach a point where the needle does not pulse, or pulses less than the other places, indicates the point of the short to ground. Shorts to power occur when insulation is rubbed through or melted, causing a circuit to receive power from another circuit. The result is improper control of one or both circuits involved. A little detective work in the form of a thorough visual inspection to determine the exact malfunction, as well as studying the wiring schematics, usually results in locating the problem. Pulling fuses from other circuits until the suspect circuit turns off also helps locate which circuits are crossed. Another short to power involves improper contact of a conductor within a given circuit. A common example would be wire-wound armatures, coils, or solenoids, where the contact point eliminates portions of the coil, reducing designed circuit resistance. In this case, an ohm meter does a good job of locating lower than specified resistance. Alternately, if correct circuit amperage is known, inserting an ammeter in the circuit will also identify shorted resistance coils in operation. You'll see higher than expected amperage in the circuit because of reduced circuit resistance. High resistance in a circuit is the kind of electrical problem that gives technicians the most trouble in diagnosis, even though the correct test steps are very easy to do. These problems are typical of dim lights or slow-turning motors. As mentioned earlier, loads in a circuit are designed to operate at a given level of voltage and current. Extra resistance in the circuit acts as if there were another load device put into the circuit. As we saw with the simple circuit, the extra load shares the voltage and current available in the circuit, thus robbing the intended loads of their designed current and voltage levels. The key to locating high resistance is the voltage drop test. Performed with a voltmeter while the problem circuit is operational, this test quickly isolates faulty connections, high resistance switches, and ground circuit resistance. Under ideal conditions, at the load device in the circuit, we want all the current and voltage that's available at the battery. Connecting a voltmeter between the positive battery post and the positive terminal of the load device will tell us if this is happening. If there is no resistance to current flow, the battery and load are at the same electrical potential level, and the voltmeter will read 0. Increase resistance in the feed side, and the load receives less current than needed, thus causing voltage to drop in the circuit. This is indicated by the voltmeter because now the battery is at a higher potential than the load device, and the difference in potential is indicated by the voltmeter. Losses of up to 0.2 of a volt are normal in low amperage circuits, such as the headlight circuit, or 0.5 of a volt in the case of the high amperage starter circuit. If the voltmeter indicates greater voltage loss, there's high resistance in the circuit that needs to be isolated and corrected. To isolate the resistance, perform voltage drops between closer points in the feed path until the voltage drop-off point is isolated. One area that technicians overlook is the ground circuit, which can also be an area of unwanted resistance. Using the voltmeter, as we did in the feed circuit voltage drop test, connect between the ground terminal of the load and the negative post of the battery. Again, you should see 0.2 of a volt or less for the low amperage circuits and 0.5 of a volt for the starter circuit. If you see a higher voltage drop, perform voltage drops at closer points in the ground path until the voltage drop-off point is isolated. One last thing about any of these electrical tests. That is, they are designed for operation between approximately 12 to 14 volts, so make sure the battery's okay. With the foundation of electrical diagnosis laid down, let's turn our attention to the mini-test. Take out your electrical mini-test and answer sheet, and let's begin analyzing the questions. For this question, refer to the corresponding graphic on your mini-test. To measure current in the starter circuit shown, how would you connect the leads? A, positive to 5, negative to 6. B, positive to 2, negative to 6. C, positive to 3, negative to 4. Or D, positive to 6, negative to 1. We see that this question is of the simple choice variety, so only one response will be correct and the others will be wrong. We know that an ammeter is connected in series with the circuit at any point, but should not bypass any components of the circuit. In this case, all responses except C are parallel connections. If the leads are connected between points 3 and 4 of the connector, we have a proper series ammeter connection. In addition to proper hookup, you should understand what the meter is reading. If the current's too low, look for resistance in other parts of the circuit or worn brushes in the motor. If current draw is too high, the motor could be binding due to bad bushings or have an internal short. Let's move on to the next question. For this question, refer to the corresponding graphic on your mini-test. In the charging system shown, the meter reading will show A, charging output voltage, B, indicator light applied voltage, C, charging circuit voltage drop, or D, ignition switch voltage drop. This simple choice question tests your understanding of schematic reading as well as electrical testing techniques and terminology. Response A, charging output voltage, which refers to output of the alternator, is not the voltmeter setup shown. To get output voltage, the meter would be connected between the alternator battery terminal and ground. Response B, indicator light applied voltage, is also incorrect, referring to the voltage level in the lamp circuit when the circuit is complete. This would be measured between ground and the ignition switch side of the indicator lamp. Response C, charging circuit voltage drop, is the correct option to pick. The meter setup shows the proper voltmeter hookup to look for resistance in the insulated feed side of the charging system. Notice anything different about this circuit? In the charging circuit, the alternator is the power supply and the battery is the load. The last response, D, ignition switch voltage drop, is incorrect. However, an ignition switch voltage drop test is important for problems such as low current or voltage in the primary ignition circuit. To hook the meter up correctly in that case, The lead should be connected to the battery and ignition terminals of the ignition switch. Technician A says, in a series electrical circuit, current is the same throughout the circuit, and there's a voltage drop across each resistance. Technician B says, in a series circuit, the sum of all voltage drops is equal to the source voltage. Who's right? A only, B only, C, both A and B, D, neither A nor B. This comparative statement deals with the relationship you need to understand about series circuits. Those of us familiar with the differences between parallel and series circuits would already be on to the next question. For the rest of us, however, let's review the difference in these electrical circuits. And don't forget, there's a task sheet covering this information. In the series circuit, we know that current remains the same throughout the circuit. Voltage varies from point to point due to the voltage drop across each point of resistance. What we need to emphasize here is that if we add all the individual voltage drops together, they equal the source voltage. In this circuit, we start with a source voltage of 12.6 volts. Measuring across our only load, we see a voltage drop of 11.4 volts. We know we need to find 1.2 volts lost in the circuit. Performing a ground circuit resistance voltage drop, we see a 0.2 of a volt drop, which is normal, but when we perform the feed side voltage drop, we see a high resistance voltage drop of 1 volt, indicating excessive unwanted resistance. Adding up the values of each drop, we see our expected source voltage, 12.6 volts. Looking back at our question, we see that both technicians are offering true statements about series electrical circuits. Therefore, response C is the correct answer for this question. We should note that parallel circuits have different properties, of which the most notable are: the voltage remains the same across each branch, current is divided. Total circuit resistance is always less than the smallest resistive branch. There's more than one path for the current to flow. The next two questions involve interpretation of schematics and application of electrical testing. For this question, refer to the corresponding graphic on your mini-test. In the circuit shown, both low-beam headlamps do not light. However, the high-beam lights are okay. Technician A says the problem could be the dimmer switch. Technician B says the problem is a defective headlight switch. Who's right? A only, B only, C, both A and B, D, neither A nor B. This comparative statement requires your ability to pick the component or components common to both the low-beam circuit and the high-beam circuit that would allow an electrical path to a certain set of headlights and not to the others. We know that the other lights in the circuit work okay. That eliminates the headlight switch suggested by Technician B. The only other component common to both sets of headlights would be the dimmer switch, as suggested by Technician A. Therefore, the correct answer to this question would be response A for Technician A only. Using the same schematic, you can consider this. In the circuit shown, all lights operate correctly except the tail lights and the rear side marker lights. The most likely cause of this is A, open in feed E, B, open in feed A, C, open in ground 2, D, all tail light and rear marker lights are blown. This simple choice question is worded slightly different in that the term most likely is used. So we may find more than one response that would answer the question. However, in reality, the chances of some of these occurring are really slim. What we do know is that in this section of the circuit, the license lamp works, so there must be feed voltage to this portion of the circuit. So response A is unlikely. Response B is also incorrect due to the fact that feed line A is in a different branch of the circuit, that portion having to do with the high beams. The last two responses could cause our lights out symptom. An open at ground circuit G2 removes the common ground for all the suspect lights. In one shot, this would cause problems in the tail lights and the rear side markers, but not the license light. This is more probable than all four bulbs blowing out at the same time, as stated in response D. So response C, open at ground 2, is the most likely cause of our symptom. Consider which answer would be correct if, in addition to the given information, you were also told that a test light connected between chassis ground and ground 2 did not light. Would your answer change? Well, yes, it would, because now we know that the connection at G2 is good. Otherwise, the test light should have lit. In this hypothetical case, then, all four bulbs simultaneously could have blown out. Other circuits to understand for the ASE tests are the turn signals, hazard lights, and stop lights. Not that they're much different than the others already looked at, but they do incorporate a few additional components. Technician A says, slow flashing turn signals can be caused by the wrong type of flasher. Technician B says, slow flashing turn signals can be caused by bulbs of incorrect wattages. Who's right? A only, B only, C, both A and B, D, neither A nor B. To choose the correct response to this comparative statement, we must understand how the flasher works in the circuit. Flashers are, in essence, bimetallic self-resetting circuit breakers designed to operate at specific amperage. When the directional switch is closed, current flows through the flasher to the front and rear directionals. As the current flows, the flasher heats up and opens circuits. Then current stops and the bulbs go out. The breaker cools, remakes contact, and the cycle repeats itself. How quickly the flasher opens and closes the circuit is directly related to system voltage and amperage flow in the circuit. A charging system which is overcharging will make the directionals flash too quickly. Likewise, an undercharging system will cause the directionals to flash slower. Circuit resistance also affects the rate of flashing. Bulbs of high resistance or corrosion in the circuit can make the system flash slower due to reduced current flow in the circuit. If bulbs of lower resistance than specified are used, the system will flash too rapidly. In a similar manner, incorrect flasher applications can cause the wrong rate of flash. Failure of one bulb in the system can cause just that one side not to flash. The other bulb on that side of the vehicle will light, but not draw enough current to heat and cycle the flasher. Looking at our question, we see that both technicians have identified one of the variables that could cause a slow flashing rate in both directions. So, response C is the correct answer. What about the hazard circuit? The hazard circuit also uses a bimetallic flasher. However, this flasher operates on a higher current draw due to the fact that both sets of signal lights flash. In addition, if one or two of the lights are out, the rest will flash at the regular rate, even with the ignition off. The hazard circuit is not controlled by the ignition switch. It's connected to the brake circuit, so that application of the brake removes the four-way flasher and the lights remain lit as long as the brake is depressed. The directional and emergency flashers are not interchangeable. The engine oil warning light remains on all the time the engine's running. Technician A says that the pressure switch might be defective, remaining grounded all the time. Technician B says that the engine could be low on oil. Who's right? A only, B only, C, both A and B, D, neither A nor B. There are three major methods the driver can use to obtain information from the vehicle, starting with simple warning lights and buzzers. The next step in complexity is that of gauges and meters, and the latest level of sophistication is the driver information system. Diagnoses of these systems begins with determining whether there's an instrument problem or an engine problem. For instance, if you have a low oil pressure light on all the time, the engine could be low on oil, or it could have low oil pressure, Or there may be a problem with the light circuit. Performing a mechanical oil pressure test will steer us in the correct direction, but if we have an understanding of how measuring circuits work, diagnosis may be made simpler. Warning lights or buzzers are typically simple circuits receiving current when the key is in the on position and grounded by some sort of switch. In the case of the oil light, a pressure switch is located at the engine block, which causes internal contacts to close when there's low oil pressure, thus completing the circuit ground. If you unplug the connector at the oil pressure switch and the light still stays on, then there's a short to ground at some other place in the circuit. If the light goes out, suspect a faulty pressure switch, which can be quickly replaced with another for a simple diagnosis. The answer to the comparative statement is C, both A and B, in that each technician states a cause for the warning light to remain on during engine running. Temperature lamp circuits work similarly, except the variable they monitor is coolant temperature, which can again be quickly checked by grounding and ungrounding the wire at the switch and checking the switch for continuity at the proper temperatures. More advanced systems use transducers to send more precise information to the driver via gauges. Transducers typically are variable resistors or thermistors which can change their electrical resistance depending upon the parameters being measured. A good example of this is a fuel level sending unit in the gas tank. As fuel level changes, the wiper contacts a different spot on the resistor, changing the resistance of the circuit. The gauge interprets this signal by varying the reading on the gauge. Sending units can be checked with an ohm meter throughout their operating range. Look for intermittent dropouts, constant open circuits, or constant complete continuity as forms of failure. Be careful when grounding a signal lead from a transducer when checking for gauge operation. Certain gauges expect to see some resistance coming back from the sending unit. Allowing complete continuity by grounding the lead could cause damage to these gauges. Which of these is a correct method for testing the instrument voltage regulator, the limiter used in some gauge circuits? A. Connect an ammeter in series with the voltage regulator. If the reading is above 5 amps, the voltage regulator is okay. B. Connect a test light to the voltage regulator output terminal. If the light flashes, the voltage regulator is bad. C. Connect a test light to the temperature sending unit wire. If the light flashes, the voltage regulator is okay. D. Connect a voltmeter between the battery positive post and the temperature sending unit. If the reading is 12 volts, the voltage regulator is okay. Many gauge circuits operate on a fixed low voltage produced by an instrument voltage regulator. This regulator reduces circuit voltage to approximately 5 volts by the use of bimetallic contact points which open and close, producing an output voltage of approximately 5 volts. This can be measured with a voltmeter. Or if a test light is connected to the output terminal, it'll flash rapidly. In the simple choice question, we see in response A, the technician is measuring amperage, not voltage, so this response can be eliminated. Response D is incorrect in that the meter setup described would be meaningless, as you are not measuring anything except perhaps continuity of the sending unit to the engine block. Response B describes the expected reaction, but the wrong interpretation of these results. So, the correct answer is response C. A vehicle shows up at your shop on the hook. The engine cranks very slowly and doesn't start. Also, the headlights become very dim during cranking. The battery checks out okay when load tested. What could be the problem? A. Worn starter brushes. B. Shorted field windings in the starter. C. High resistance in the starter ground circuit. D. None of the above. This simple choice question is a little more complicated than it first appears, for both technical and grammatical reasons. From a technical standpoint, we must understand the symptom. That is, the starter system cranks slower than normal. This can happen in 4 ways. The first is a low battery state of charge. The second possible cause is high resistance in the starter circuit, not allowing sufficient current to the starter. The next possible cause is that there's a short in the starter circuit, and the last possible cause is a mechanically binding engine. The low battery state of charge was eliminated by the load test, and a mechanically binding engine was not even given as a choice. A hint in the question indicates whether there is a low resistance problem, such as a short, or a high resistance problem, such as a dirty connection in the starter circuit. The statement about headlights dimming during cranking indicates a large amperage draw. So we're looking for a cause of very high amperage draw in the starting circuit. Looking at our choices, response A suggests worn starter brushes. That's right, brushes, not bushings. Worn brushes would reduce contact with the commutator, lowering the amperage flow through the starter. Yes, if the response had said worn bushings, then it could have correctly answered the high amperage draw scenario. Read carefully. Obviously, response A can be ruled out. Jumping down to response C, again, we see high resistance in the circuit, which we've already ruled out. So the choice boils down to response B, shorted field windings, or response D, none of the above. Response B, shorted field windings, can cause a slow crank, high amperage draw situation, and therefore is the correct response. Well, that's about as complicated as they come, at least for a simple choice question, that is. The next starter question approaches the same subject from a slightly different angle. Test results for a starter amperage draw test indicate unusually low readings accompanied by slow cranking speed. Technician A says that a possible cause could be poor commutator or brush condition. Technician B says that the armature rubbing on the pole shoes could be a cause. Who's right? A only. B only. C, both A and B. D, neither A nor B. This comparative statement once again tests our understanding of electricity, circuits, and amperage relationships within a series circuit. We know from the test that there is lower than expected amperage flowing through the starter motor. For this to happen, there must be increased electrical resistance in the starter circuit. The choices offered by technicians A and B at first don't appear to indicate extra resistance, or do they? Poor commutator or brush condition reduces the contact area between the brushes and the commutator surface, effectively reducing the amount of current that flows through the starter. And anything that reduces amperage flow increases the resistance in the circuit. So this statement's true. Now, if the starter armature were rubbing on the pole shoes, there would be mechanical resistance to the starter turning without an increase in electrical resistance. The overall effect would be higher current flow to keep the motor turning, which would show up as higher amperage draw readings than expected. So technician B's statement is false. So the correct answer is response A, for technician A only. The last area that we'll look at is the charging system. The charging system has changed significantly over the last several years. The main change is from DC generator systems to AC alternator systems. You should be familiar with the differences between the two for the test. We'll concentrate on the more popular alternator systems in our discussion. In an alternator, the brushes carry A, output current, B, stator voltage, C, field current, D, none of the above. This simple choice question tests your understanding of the components that make up the individual electrical circuits in the alternator. The brushes, as you recall, contact the slip rings on the rotor assembly. When current is passed through the rotor, it becomes an electromagnet. When this magnetic field is rotated inside the stator, AC voltage is produced in the stator windings. By altering the strength of the electromagnet, output current flow is regulated. The brushes feed the field windings which produce the magnetic field. The slip rings, therefore, only carry relatively low amperage field current. Electrical output from the stator windings, once rectified by the diodes in the rectifier bridge, is the high amperage output current which is measured at the battery terminal of the alternator. So the correct answer to this question is response C, field current. Technician A says the alternator doesn't produce AC current until the stator windings are fed battery voltage. Technician B says the alternator doesn't produce AC current until the field windings are fed battery voltage from the regulator. Who's right? A, Technician A, B, Technician B, C, both A and B, D, neither A nor B. This comparative statement tests your understanding of how an alternator produces alternating current. As we stated in the last question, the alternator produces AC current when the rotor's magnetic field is rotated inside the stator windings. To make the rotor into an electromagnet, current must flow through the field windings. This current flow is controlled by the regulator. Looking at the statement, Technician A's statement regarding the stator winding is incorrect, and Technician B's statement is correct, describing the proper operation of the alternator. So the correct answer to the question is response B, Technician B only. A field current draw test can be performed on an alternator to find A, grounded field windings, B, a shorted rotor, C, poor brush contact, D, all of the above. This simple choice question tests your knowledge of testing procedures for alternators. The field current draw test involves the measuring of the current in the field circuit of the alternator without the engine running. Again, using our electrical circuit basics, poor brush contact or high resistance connections will show low amperage flow. High amperage flow could indicate other electrical faults, like a shorted or grounded rotor field coil. So the correct answer for the question is response D, all of the above. We've covered several key questions about automotive electricity in this video. There's a lot of information to look at, so if you feel you need more time on this extensive test topic, please go back and review. Remember, proceed through the program at your own pace. If, however, you're not up to speed, now's the time to get some additional help. There are many good books and video programs available on automotive electricity. The reference sheet provided in your support package lists some of the better programs. The rest of the mini-test questions are analyzed in your support material. And don't forget, the task sheets are still an important study guide on this subject. You've made the right move by getting involved with ASE certification and have shown even better judgment by trying to prepare properly for the exams. You'll do fine on the test. Review what to do on the day of the test on the introduction video and test-taking task sheet. Knock 'em dead.